Good morning, everyone. Welcome to the GIST Sea Level Rise seminar. We're very glad to have Dr. Beata Csatho today. She's a professor in the Department of Geography at the University at Buffalo, and her research interests focus on monitoring ice sheet mass balance and ice dynamics to understand ongoing rapid cryospheric changes. In particular, her research focuses on combining geophysical remote sensing, climate, and glaciological observations to understand subglacial geology and ice sheet dynamics. Also reconstructing historical cryospheric changes and developing new methods for change detection, data fusion, and visualization for its science application. She is a member of the NASA Sea Level Change Team and was a science team member for NASA's IceSat, Operation Ice Bridge, and ICESat-2 mission. Professor Csatho earned her PhD in geophysics from the University of Miskolc in Miskolc, Hungary, and was previously a research scientist at the Bird Polar Research Center at Ohio State University. And today she will be speaking on new observational constraints on ice-ocean interaction on the Greenland outlet glaciers. So welcome, Bea.
First and foremost, I'd like to thank for the invitation. I am excited to show results which are results from many years of work, some published, many of them still in progress. First and foremost, I would like to acknowledge our team, which is at the University at Buffalo, especially the students and postdocs, some of them who is here with us today. And also, there is no research in these days without a wide collaboration. So this is not an exception. So I listed many of our collaborators. If I have missed somebody, please, it's just because of the broad nature of this work. So I was hesitating how to call this presentation. I ended up using these observational constraints. The ultimate goal is better understanding processes, but we are not yet there. So the first goal is really generating this continuous spatio-temporal reconstruction of ice sheets coming from the far past and eventually going to the future as providing help for numerical modeling through assimilation, validation, calibration using observational data. However, an even more important and difficult goal is attributing of the observed changes to processes and hopefully using those attributions to improve process modeling and, again, projections. So observations can be grouped in many different ways. One way of grouping observations of forcings and constraints about ice sheet conditions. These ice sheet parameter can be about ice sheet geometry, ice flow, elevation velocity, in glacial, proglacial, basal properties. They can come from remote sensing, in situ observations, and also they can come from glacial geological record. In this particular talk, we will be focusing on ice sheet geometry, especially as it is reconstructed from altimetry and DEMs. So I also focus on outlier glaciers in Greenland. Since ice and ocean interaction, I am citing McCormack, ice-ocean interactions dominate the current ice loss signal, and they are really still poorly understood, despite of the enormous progress. And remote sensing is providing comprehensive data sets. However, this comprehensive and huge data set is coming from multiple sensors, disparate sensors, and there is still a need for fusing and reconciling those data. Progress in fusing, reconciling, combining will help in better understanding processes, especially as AI, machine learning, especially physics-based approaches are now available. Ice sheet surface elevation provides information in two ways. One is measuring the current ice sheet surface and also the different features on the ice. However, also elevations and DMs around the ice sheets have records of previous ice surface through the records of moraines, also records of vegetation cover, erosion, and other features. This picture just showing a few of those. So I will build this presentation in two ways. One is giving background on the toolboxes we have developed in the last, now 15 years, but also use those toolboxes to show examples when the data and tools were used to reconstruct changes in different parts of the Greenland ice sheet. But before going there, I want to start with a long-term reconstruction, which is a paper which is now a few years old, which combines reconstruction of the Holocene starting 12,000 years ago with projections of future changes using numerical modeling, which is constrained ice marginal moraines. I like this example published in Nature with Jason Breiner as a lead on that because it really shows this intimate relationship between observational record of the past and present and the modeling, which will help us to better understand the future. The message from this particular paper was that projected changes based on the different pathway scenarios expected to be larger than changes which occurred anytime during the last 12,000 years. After this broad background, let's go and focus on the present and see what we can learn from the instrumental record. So I start with a reconstruction, which is probably very familiar for very much everybody on this call. But first and foremost, I want to emphasize that we are incredibly lucky working in Greenland because of the exceptional observational record for ice sheet surface elevation. So showing on the Arctic report card as the annual mean surface air temperature anomaly, and the red one is showing the Arctic and the polar amplification. And this curve has a few major features, has a couple of warm periods. One is around 1940, followed by a colder period and a rapid increase in temperature. And above it showing the different type of data sets which are available for reconstructing ice sheet surface, starting with the first topographic mapping in 1930s, followed by model stereo images, aerial photographs in the 70s, 80s, and then came the widespread use of airborne and satellite remote sensing, starting with the first LiDAR measurements in 93, followed by the different freely available satellite imagery like ESTER and high-resolution accurate ones like WorldView and GeoEye, and of course the triple combination of NASA's missions with ISAT, ISAT-2, and OIB, which provides a precise reference frame. I skipped this one. This is just giving lots of background information about the exact availability when all these different sensors collected data. I want to emphasize that although I am talking about laser as the reference frame and reconstruction and DMs, of course, there is also radar altimetry and other incredibly important set of observations. However, fusing laser and radar is still an ongoing research, active research. And as you will show, the details what we are teasing out from the DMs and laser altimetry data are probably beyond the resolution of what radar can produce. And I just want to shout out for NASA for providing not only ICET and ICET-2, but the Operation Icebridge mission. As Patrick introduced me in the beginning, I was part of the science team of all three missions, and it was super exciting to see how all these pieces come together, providing this uninterrupted or not, although not always continuous record of Greenland. And on the right, that's ICET-2, launched in 2018 on the last Delta II rocket. So let's first start still a little bit a longer period. So Little Ice Age. As the temperature records suggest, there were a few periods of relatively high mass loss, most notably around the 1930s, preceded the more recent continuing increase in temperature. We had used very much all the available record. It's kind of an example what one can do, taking it all together for Jakobshavn. So the surface change here is shown in two places. Number one, but the ice retreated, to number two, once the ice retreated beyond number one. And the different colors are showing different data, starting with glacial geology, continuing to altimetry. And as not a surprise, there is a broad agreement between the lowering of the surface and increasing air temperature. This is from Illulisat. Especially, you can see the rapid increase around the 30s, which was coinciding with a relatively quick drop in surface height. However, the rapid thinning in around the late 1990s was unprecedented in the amplitude and also the duration of that thinning. So moving to our toolbox. So we have quite a few tools in our toolbox. The most important ones I am mentioning here are those which are combining altimetry data. That was especially crucial when ICET didn't provide exact repeat. Now with ICET-2, reconstruction is easier, but we are still feeding everything into the surface elevation reconstruction and change detection solution, and working on currently adding radar altimetry data. Altimetry, again, before the ICET-2 era, laser altimetry provided very bad sampling in space and time. It is irregular with big gaps, so normal interpolation methods didn't work well. So our group developed an approximation technique used by localized panelized splines. These are not simple splines, but these are spline-based solutions to interpolate in time. I will use this in all the results I am showing during the rest. And the last part of this toolbox is Mulan, which is an automated open source tool for ultraglacial elevation change detection. It's using not only fixed surfaces, but using altimetry as a so-called dynamic control to correct DMs, and using it, one can achieve sub-meter accuracy, a few tens of centimeters. And it's an open source toolbox which we are currently deploying on GHub, our cyber infrastructure project. Very quick introduction to these different tools. I will go quick so that I have time for results. So SARAC is a typical fusion engine for altimetry, which is simultaneously reconstruct the surface shape and the elevation. We are usually assuming that the surface shape doesn't change and the elevation varies. The advantage of SARAC that there are two, compared with some of the other approaches, that our reconstruction works in an absolute space. So it's not a relative change, it's reconstructing the height of that patch on the WGS 84 ellipsoid. The other is that we are reconstructing heights for every epoch. Whenever data are collected, there is a corresponding height in that absolute space. These two features are absolutely necessary to identify the fine details of surface elevation changes. Any altimetry reconstruction, when you see one time series, it looks simple. It has maybe 20 points, but actually it's using hundreds and thousands of points. So this one is an example of one patch. I will show lots of things for Jakobshavn. So it's in the Jakobshavn region. The different colors are showing different sensors. That 1 square kilometer patch has many thousands of data, and at the end it shows a single time series with arrows for reconstructed elevations, so small that it's too small to show. It's about 10 centimeters or better. And just an example of ISET2, we all love ISET2, that's just the photons showing the crevasse surface. Alps, I don't spend much time on Alps. This example shows nicely the irregular sampling, and that the spline base interpolation has a variable width of spline base, which gives a reasonably good continuous reconstruction. Advantages are that it provides error for the reconstruction for the interpolation. And since it's a continuous reconstruction, one can compute derivatives. And also one can play with the fitting to make it more closer or more smoothing. And one can use it for not only surface elevations. On the right, you can see examples from surface elevation, velocity, and halving front location. Moulins. So we want to correct DMs. And we also want to study floating ice. Working on floating ice requires a few additional processing steps, both on altimetry and DMs. One is tidal modeling, tidal correction, and the other is inverse barometric correction. Without going into details, the upper curve time series shows the uncorrected elevations from altimetry and DMs, and the lower one is after the tidal and inverse barometric correction. So it vividly shows how these corrections are removing the surface changes which are due to these short-term geophysical processes. So I mentioned in the beginning that DMs are corrected in what we call like a dynamic control point data set. It's actually not control points, but dynamic control time series data set. Left side is showing altimetry. So look at the circles on the left side. Those are all ATM airborne altimetry data. And the DEM and ISET with the triangles, and also DEM's answer and spot. You can see that the squares and the crosses are really off from that nice smooth change curve defined by the altimetry. We assume that those differences for the DMs are due to errors in the DMs, and we use those so-called error vectors to correct the DMs using simple transformations. So this pair is showing a before and after. So after the correction, which is a simple polynomial transformation, everything beautifully lines up, and the DM error indeed decreases to typically to sub-meter. What else can Moulin do? We also added a new routine where we actually account for short-term changes using firn densification models, meaning that we can remove all the short-term changes, both from the altimetry and the DEM, again, to improve the fit. This little figure on the right shows a time series when we have an undersampled surface variation due to surface processes, and at the bottom, when all those processes are removed, there is a much tighter change, which then will provide better correction. Remember, if we do this, then we also have to remove surface changes due to surface processes from the DM, and eventually we can add it back. So lots of tricks to be sure everything is precise. We can also see that not all surface changes due to densification SMB. On the right side, we see temporal variation. After removing surface processes, we still see some variations, such as the seasonal variations in dynamics. So let's take it all together. What we get is a time series, and there will be many of these kind of plots from here. So we take the surface change from, in this talk, it will be mostly altimetry, and then take the surface change due to surface processes from different FDM models, RECMO-GEM, and other FDM. And then the difference of the two will provide a dynamic change as a function of time. I want to emphasize, or I want to ask you to pay attention to Hui's presentation. I am using her curves. So she was doing the entire Greenland processing, computing all the dynamic changes. And she will have a poster presentation at AGU showing reconstructions on drainage basin scale and analyzing, and hopefully showing some, which you find interesting, new conclusions about Greenland changes in the last 30 years. So this is her side. Again, just going through the different steps. What is important that once we get the time series, we not only partition to dynamics and surface processes, we also account for the GIA for any kind of glacial isostatic rebound, and also we do elastic correction to get mass, and at the end compare with grace. I am skipping here because I want to go to results. So if you take changes, mass changes, which are partitioned into dynamics and surface processes on a drainage basin scale, you can see that most of the variation, not surprisingly, coming from the surface processes, the orange one, and the dynamic changes on a drainage basin scale are very smooth, showing typically 1 or 2 cycles, like rapid thinning in southeast, and then kind of stabilizing, and then other thinning phase. And I think everybody, so I want to talk from here about changes in ice dynamics. And what you can immediately say, well, there is so much uncertainty in this partition. So are we worried about that? And what kind of conclusions can we get? And yes and no. If you take the absolute value of ice dynamics, this is again from who is showing dynamic changes in a drainage basin scale, and blue, the different solid and dotted and the dashed lines are dynamics. Yes, the partitions are very different if we are using IMAU, Goddard, or GEM. However, when we will look at the small short-term variations, those variations are actually very consistent. So here I am showing a few examples, and I will show this kind of plot. So let me just once more repeat. So the upper part is always the elevation change in an absolute space. The second one, FDM, and now you can see that it includes all 3 different FDM models. And the last one is dynamic thickness change interpolated by Alps, showing the uncertainty of interpolation. So this first example, Jakobshaven, near the calving front and further upstream. And what I said is illustrated nicely here, that all the little wiggles on this dynamic thickness change curve are very much identical. And even if there is a difference, and it's actually not so small, because one step here is 25 meters, still the shape of the dynamic change, the short-term variations, is very similar. suggesting that many of the differences are coming from the reference period for the FDM and other processing steps. Okay, so I was showing Jakobshavn has a huge dynamic change. So maybe that's not the case if we go to places where dynamic changes are smaller. Maybe those differences in the short-term pattern are kind of like hidden because of the large changes. Not quite. So this other example is Szermec-Avannarlek. It's one of the glaciers I will show more examples. It's draining to Tosszukatak fjord. And surface elevation looks in a way very messy, and partially because the surface elevation changes in similar magnitude or even smaller than the variation due to FDM. But again, the dynamic change, there is a shift, there is some difference, but it's actually very similar, regardless of which firn densification model we use. The patterns are very stable. So, second part, results. So I promised to give constraints, observational constraints, and some hypotheses not really proven yet from altimetry and dynamic changes, especially for ice-ocean interactions. Couple of things which are important, which we don't have time to get deeply into. Well, Greenland is surrounded by different ocean currents with a complicated set of surface and deep ocean waters with different temperature regimes. And other glaciers, what is usually gets more attention is the frontal ablation and overcutting. But actually, Greenland not only has a few longer ice tongues, like here we show just a schematic for 79 North, but as outer glaciers are retreating, they often develop short ice tongues which are breaking up by the end of summer. So, Jakobshavn. So we are back to Jakobshavn showing that long retreat, and what we are focusing now, what kind of processes we might see on the dynamic thickness change time series. So we are back to that long-term elevation change, but now we are focusing with the results to the altimetry period. So let's start first just with the calving front retreat. So Jakobshavn started to retreat in 98, quite rapidly retreated until 2004 when it had a relatively stable position with a large seasonal variation, further retreat and advance. If you look at interannual seasonal variations, you can see that rapid retreat, stabilizing, further retreat and advance with varying seasonal pattern. So let's see how that looks on the altimetry record and the velocity record and the calving front together. So for starting, they all show similar behavior. Again, not surprisingly, there is rapid thinning during the period, especially after 2012, the big melt year. There is also rapid ice flow speed up during the same period, and this is followed by a slowdown and thickening attributed to ocean cooling. So one thing one can learn by looking at these detailed dynamic thickness change curves to see which of the processes look like a diffusion which is propagated up, and which of the processes look more local. So we are starting from the calving front, going up, and of course we see that overall retreat-driven thinning in the beginning. There is a very widespread 2012 rapid thinning, and however, the cooling in 2016 seems to be less pronounced as we are getting higher up, suggesting that that's probably more a local process around the calving front. So my first interpretation a few years ago from an LGU talk was that we had this retreat-driven thinning. There was a short pulse, large thinning, and that is very clear in the annual rates. So the diffusion pattern 2004-2005 was concentrating more on the fast-moving part and decreased very quickly inland. You could also see the decrease of this diffusion pattern in time in the annual rates. However, this 2012, 2013 short pause was kind of shooting up all the way on the glacier. And before and after, there was a complex pattern beyond the thickening. So, revisiting that complex pattern. And as you look at the lower part, so number 1 and the other is number 2 upstream, now you see much more details. I'm kind of going back and forth. Why do we have that? Part of it is because we have lots of data from ICET2. The other part is that Hui made a great job to find the best place with very high point density. So looking at these two different time series, you can see striking difference. It's not only the sampling, there is just much more happening on the time series near the calving front, but both show a few common behaviors. And let's jump to the result. So what do we see on this time series? One is, of course, we see this nice smooth calving front retreat-driven thinning. 2012 is that thinning signal, which is after a large melt here, which is shooting up high on the ice sheet. That's that blue arrow. And we see a similar event in 2019, the other blue arrow, which was another big melt year. And I attribute that more because of the big extent that it's not so much just a calving front and propagating upstream diffusion, but also a big part could be shear margin weakening due to that large melt and runoff. 2016 ocean cooling was first described by Ola Kazandar in 2019. The dynamic thickness change records suggest the potential second period around 2022. What is also interesting, the short-term variations. I marked one around 2016, but they occur everywhere. And it's a seasonal pattern, but it's not there in every year. And potentially what it could be these changes in calving rate, which is controlled by rigid melange, as described by Joaquin et al. In 2020. So my interpretation is that the broad scale changes, which are also visible on higher elevation on the ice sheet, are more related to calving front retreat, shear margin weakening, and ocean cooling, while the superimposed short-term variations are the ones related to changes in calving rates controlled by rigid melange in the fjord. Cooling, there is a recent paper which attributed potentially this cooling to the Baffin Bay polar water, which in recent years have been detected in West Greenland. So a potential interpretation needs more work that the 2020 dynamic thickening could be another cause of this Baffin Bay polar water reaching the Jakobshavn fjord. So my next and last example, we are going to the north, and it's a complicated story. So I try to make it simple, and questions at the end are welcome. So I am back to that figure which we published in our 2014 paper, and I enlarged the region just north of Jakobshavn because it was so complicated. So the different symbols are showing outlet glaciers doing different dynamic things. And if you look at the symbols, they are more or less kind of organized in some pattern, except in this region. Here you have outlet glaciers draining in the same fjord. Some of them is thickening, thinning. I also had something I called unique behavior because it was so weird. So because of this complexity and the time series at that point were very short, we wanted to go back and take another look at this region to see if there is an explanation of this complexity. So glaciers here, ekipszermia, I call it ES, Kangilen, Gataszermia, KS, Szermek, Kujalek, SK. They are mirrored, the name, and you will see that the behavior is also almost mirrored, and Szermek-Havanarlek in the north. And just a reminder from Jeannie's paper that we expect to have all these processes acting here. So controls could have frontal ablation, changes in subglacial discharge, also retreat-driven thinning. So there is just this broad range of different processes. And the question here, can we use the observational record to build up some hypotheses which then can be tested later? So I love this figure from Mike Wood showing the different type of glaciers, and we have all of them. So Kangilen-Gataszermia is a deep one with undercutting. Szermek-Havanarlek and Szermek-Kujalek, the ones in the north, are calving on a seal, and ekipszermia is calving in shallow water. As a reminder, Jakobshavn used to have a long floating tongue. So let's go step by step. So we start with ekipszermia. So reminder, that's a glacier which is shallow. It actually sitting on a seal, and it's fully calving into cold water. It's a beautiful time series which was captured by Luthi et al. I think it's 2011, that the thinning of this glacier is very much retreat-driven. The retreat might have been, so there was an increasing negative surface mass balance, which could have increased crevassing, increased calving, or it could also slightly decrease the height, and it could float and get closer to flotation. But anyway, so this glacier had a simple, beautiful cycle of dynamic thinning. However, one has to continue. I don't have the recent ice set point yet to see if it's starting another cycle. I am always surprised how quickly these glaciers really find their new equilibrium. Okay, complication. Wherever you go in Greenland, you see complicated things. So if you go higher up on ekipszermia, this is referring now to Robin Bell's paper in 2014. She was looking at ice-penetrating radar profiles and showing what she considered basal units and basal free zone. And the altimetry, and this is probably the most southern region where she detected this. So suggesting that it's a complicated region. Well, you can see that also on the altimetry. So dynamic thickness change quite far from the coast. 21 kilometers typically when you get that diffusion thinning this far, when the velocity is also low, would more or less disappear. No, there is a significant dynamic thinning, which could be up to 20 meters in 15 years. And it's also very complicated. So the surface is going up and down. Simple way, how I always look at this region, it looks like that there is just lots of water sloshing around and also freezing on and melting. So let's go to the next glacier. So that's Kangilen-Gataszermia. And I included Jakobshavn for reference. What you see on Kangilen-Gataszermia, that it started to thin in a relatively unexpected time. Typically, what we see in this region is more like Jakobshavn, when it would start earlier in 2000, or something which is very clearly retreat-related. It started to thin in 2008. And the next one is doing the opposite. Rather than starting to thin in 2008, and they are very close, draining in the same fjord, it started to thicken in 2008. And this is one which is calving on a ridge. So two glaciers next to each other doing the opposite. So what is happening here? It's very clearly not only climate-driven or ocean temperature-driven. So one possibility is that there is some hydrological connection between these two neighboring basins. And the middle shows that topography. You can see that they are really not divided. They are very much connected. And both the velocity and the thickness changes and the reconstructed drainage suggest that there is water piracy between these glaciers, and rather than seasonally, interannually, water might move more in SK or in KS. But let's go back to the time series. So potential water piracy in 2008 causing thinning of KS. 2012 melt is intensifying it. And remember, this is a glacier in a deep, warm fjord. So it could be that it's showing the same ocean cooling effect around 2016 as Jakobshavn. So looking at map views, so between 85 and 2008, there was thinning for both glaciers. However, between 2008 and 2014, SK stopped thinning. We already saw that here on the time series. Now we can see it for the entire glacier. The entire glacier is kind of stopped doing anything or slightly thickening, while the neighboring glacier, KS, was thinning rapidly. And if we look at the velocities, SK was going really fast around 2000. However, it really slowed down after that. At the same time, KS was speeding up. So contrasting behavior in velocity, contrasting behavior in thickness, a very, very weak divide. And what I love is this, it's like velocity difference, which is showing some really intriguing structures between the two glaciers. We also did a reconstruction, and that's where DM corrections are important, and we still need to improve it and add more DMs. But again, what it very clearly suggests that the connection between the two glaciers is possible. And in 2014, that we have to redo it. This was from Arctic DEM, so it's probably not precise enough. But there is a suggestion that there was indeed a rerouting. And what we believe is happening is this periodically connecting and rerouting as the ice surface developed due to slight small changes in surface elevation. And showing again the drainage pattern. So you can see that more drainage is going into the glacier, which is speeding up. Here that was SK, Szermek-Pujalek, and here it was Tangilek-Lemgata-Szörmia. Just a reminder that there is a lot one can see in this time series. However, in places like Szermek-Avanarlek, you move a little bit and your time series can be very different. And before I conclude, I also want to say that we have here, we were looking at only one data set. Very detailed time series, but only dynamic thickness change. Of course, we have lots of unknowns. So going from these, what I presented are, I wouldn't even call them interpretation, but more hypothesis. This might happen, that might be, but it requires taking a much more complete, comprehensive look at these regions. However, dynamic ice thickness changes really help to develop those ideas and also highlight those regions and those processes which are occurring even on short time scales. So concluding, so it's possible, and there are nice papers showing that one can go back all the way to the Little Ice Age or beyond using historical data and also glacial geology. And those long-term reconstructions lack the details, what one can do with the satellite data set, but show a good overall agreement with the temperature record. And I am very cautious. So dynamic thickness change record of Cermak-Jakobsheim reveals change patterns that might be attributed to specific atmospheric, oceanic, and glaciological processes, like the cooling from the Baffin Bay deep water or changes in calming rate in rigid melange, but of course, more work is needed. Again, being cautious, we detected rapid reorganization of ice flow and potential subglacial water piracy. Again, more work is needed, especially densifying the DM time series, having worldview GeoEye and ICEL2 together really facilitate those type of studies, at least for the last few years. And I want to thank to NASA, NSIDC, NOAA, PGC for data and for my group and for all the collaborators for participating in this work. Thank you very much.
Thanks very much, Bea. Do we have any questions? Yes, Jeff has a question.
Hi, thanks for the talk. I wonder whether are you attributing these changes mostly to ocean temperatures, the thickening and such? And since the ocean original warming, like at Jakobsheim, was detected using temperature sensors on trawler nets, I wonder whether you've got any such data available for the period of thickening and again thinning.
No, I am looking for those type of data, but I think these kind of reconstructions are also important because some of the plans, and I know Dennis is on, so some of the plans for ISMIP-7 is like propagating shelf temperatures and salinity profiles to the fjord. Those data which would connect the fjord temperatures, ice shelf temperatures, and thickening thinning would be really crucial for improving the different ways of projecting and modeling these processes.
Yeah, thanks.
And Robin has a question.
You can hear me? I have bad internet today. I'm wondering what you think. Beautiful talk, by the way. Thank you. I'm wondering what you think the impact of the smoothing in the bed machine topography is on your water piracy result. Do you think it's robust enough, or is that smoothing likely to impact things?
Yes, so we keep checking bed machine and how well we can use also for grounding line positions. I know that we always need to be very careful because we also use flotation criteria to get grounding lines, which can also suffer from bed machine. I think looking at the radar profiles, I would be more concerned having similar conclusions in Southwest Greenland, where those radar profiles are really very noisy and incomplete. And what we do, we haven't done it yet, but we are going to do next is doing comprehensive Monte Carlo simulation, but we want to have as dense DMs, surface DMs as possible to look at how robust it is. I would think that we will have this potential of rerouting. How robust it will be remain to be seen.
It might be worth, having just been looking in that area and seeing the big differences between bed machine and the raw picks, it might be worth looking at the raw picks out of Croesus in the critical areas to see how robust they are right in the places that you see the switches.
Thank you. That's a great recommendation. And ideally, I have been showing some of these results in an HEU meeting, and what also came up, it would be really interesting to know more about the bed. Like, is it sediment? Is it crystalline rock? And also this region is very much, there are a few papers about bed conditions, warmer and colder, and we are exactly in that transition zone. So we are in a climate and the bed transition, but thanks for the recommendation. And Robin, when you detected, can I have a question back?
Sure.
When you detected that basal frisson, it's kind of like sitting on its own. Do you think that with the more complete radar record, we might find more of those in this region?
I've been looking at that in the last month, and first, I think we can see that one move in the decades worth of ice bridge data. So I think that's an interesting thing to compare with your results, that basal unit actually moving down slope. And I think there is evidence for other smaller structures in that region. You need water and steep topography facing inland to make them.
So we were showing this, but I was also looking at run edges, and we see many of these really complicated inland dynamics thinning time series where this basal frisson or these basal units are. So there should be some kind of process connection. And hopefully we can keep going, trying to tease on more and more.
Beautiful work. Thank you for showing it.
Okay, do we have any other questions? Like the question.
Yeah, Beata, thanks for the talk. I was wondering, so first about what you call the dynamic signal. Am I right to understand that this is basically a residual after removing firn compaction, SMB, like the surface terms?
Correct.
Yeah. And then a step further, do you think that this is really what we ought to compare with? But can we compare that to models? Is that, is that the same thing that we would get if we remove a surface mass balance signal from a modeling results? So that's kind of the direction where I'm thinking if we, yeah.
Yeah, excellent question. Dennis is on the call with Dennis and Sophie Novicki. We have these endless discussions, like what is the best to do? Like, should we compare the surface change? Should we compare the dynamic change? I think Sophie is leaning to the direction that it might be a more robust comparison to try to, and I don't know, Dennis might have some comments on that. And it's really, I find it shocking how similar these short-term signals are, regardless what FDM we use. Of course, one can always be very skeptical to say they all could have similar problems. I don't think so, because they have different forcings and they have different form modules. So I think especially the pattern is very robust. And when you use model, you anyway do some kind of normalization. So But my concern was, as I keep reading the literature, that normally the modeling papers are telling, oh, like the CHOI paper, we cannot get the ocean cooling because our models are not accounting, and especially these tiny little variations. So what I am hoping that these results can at least be used to help to constrain ice-ocean interaction as we are moving toward this MIP7.
Okay, thanks.
Yeah.
Okay, any other questions? We're almost at the hour, so, I guess if there are no more questions, we can stop there. So thanks again very much, Bea, and thanks everyone for coming.
Thank again for everybody and for Patrick for the invitation, like always. It's so good to have a push to sit down and think about what we are doing and why we are doing. And thanks so much for listening and for the great questions. And hope to see you soon, all of you.